it, so I'm going to come in pretty loudly. How's that up the back? Zachary. Zachary up the back. Can you hear me? Because last week's lecture didn't get the audio on it, because I think this wasn't working, this particular mic. So I've gone to the lapel one. So does that come out too loudly? Is it all right? Real good? All right. Lights okay? Action. All right. So guess what, guys? We are into the second part of this geometrical application. So first part, last week, all about finding derivatives. Just giving you a heads up. Remember that when you do the quiz this week, any type of derivative could come your way. So remember those rules are important as well, okay? As well as just your basics, especially that index, testing of your indice knowledge, righto? So this is what we've got. We're sort of rolling over. It's very similar to last week. We just do a lot more of us practicing today. So it's got there on page 16. Sketch this function. So we're looking at higher order polynomials, greater than 3. Now some questions in the tutorial will still have a degree of 2 and a degree of 3 there for the next section, but we want to tackle some of these that are greater than 3 and see what happens. Now it's all about the setting up, okay? So it's not just about the drawing, it's about you showing me what the stationary points are and how you've tested it. All right, so back on page, you remember the little flow chart that was on page 6? That's pretty much what is in our head this time. So on page 6 there's that flow chart, tells you which sort of path you should take. All right, so keep practicing that flow chart, put it into action as we go. Here's the first one. Now it's been done for you, but I want you to highlight anything that you think is going to be vital for you to remember. First of all, it says, okay, that you want to find any turning points and points of inflection. And quite often in this sort of section, all right, it says no need to find the x-intercepts because they become too hard to solve for us. So we're not concerned with where they cross the x-axis. We are concerned to where they are turning and the points of inflection are. So you generally start off, you go straight into first derivative and second derivative, so they come out pretty quickly. It then says, this is where you take over. To find a stationary point, you need to be able to say, I'm going to put y dash equal to 0. And state that to yourself, because I will find people putting the wrong function equal to 0. This does not say put y equal to 0, doesn't say put y double dash. It says what you have as y dash. So you put your y dash equal to 0. Before you tackle that equation, which you don't want to tackle, your factorising skills should come into play. Highest common factor should be called upon because it will make your life a lot easier. So you can also divide by the 12. The 12 doesn't need to be there because it's an equation now. Once you factorise that, you get yourself 3 answers, 0, 3 and 8. Now you have not finished at that point. What we found last week in the tutorial, the worksheet that we were doing, people would find the x values and then walk away. These are points. So you must find the y value. Now remember, you are finding a y value. So you go back to the function that has got y equals. Now I'm stressing that because if you label your y dash, y double dash, then you won't have a problem when you go back up and substitute. So we're about to substitute into y. Here comes the first one. When x equals 0, now suddenly in the book they've just got the answer. But on this slide, it's been able to substitute the 0. Even though you think it's really monotonous, it makes an important step in your calculations because if you get one of these numbers wrong, the diagram's just not going to help you out. It's not going to agree with you. So the first one is 0, 0 by the looks of it, and then they've tested out their second derivative. Again in the book, it just says y double dash is greater than 0. That didn't just appear from nowhere. All right, what you've got to do is substitute 0 in and you get your 288, which is greater than 0. So it's been summarised in the book. So don't just think, oh wow, you just get them from out of the air. Like you have to do some substituting. And because y double dash is greater than 0, then it's going to give you some sort of minimum. So you can state, the summary says minimum turning point at 0, 0. Now it's the next one that, again, if you look at your notes, it says when x equals 3, it then says y equals 351. Bang, just like that, magically. It doesn't happen magically. What has happened is we've substituted the 3 into the y function, and we've got that 351. So can you see what I'm saying? It doesn't show it in your book, just to help summarise, otherwise it takes us a lot of pages to do it. So otherwise it just says bang, it's 351, but there's been a method to it. Also at that particular point, y double dash, all it says in the book is y double dash is less than 0. Where'd they get that from? They substituted the number 3 and they got a negative 180, which they've declared is less than 0, which you now can say is giving you a maximum. All right? And the third one, same as that, I'm not going to emphasise it all over again, but it says when x equals 8, the y value comes out to be minus 1024. The second derivative gets used, and it's turned out to be positive, so there is a minimum. So summarised, on page 16, you can see it summarised. There's a minimum, there's a maximum, there's a minimum, okay? If any of those numbers go wrong in your calculations, your diagram just won't look, you know, it may not even agree. You may not even be able to get the curve happening. So this is what it says. Now you're looking for points of inflection. Now remember, this is still good revision for last week. That means good revision for the quiz you are about to do this week. It says if you're looking for any points of inflection, any points, whether they're horizontal or non-horizontal, why it's saying non-horizontal there is if it was a horizontal point of inflection, it already would have popped up as our stationary point. So that's why it's declaring it there. Oh, now we're just looking for any non-horizontal points of inflection. When we do that, what ends up happening is, again, when you get this equation and you have to solve it, this is probably the hardest part for you guys. You get the second derivative, you put it equal to 0, you stare at that and go, wow, how am I going to do a factorise with a 36x squared? Quite hard. Make life easy for yourself and look for a divided by something, even if you start with 2s or 4s. So that way you can get yourself down to this statement, which is that one that needs to be attacked by a non-monic trinomial. So some semester 1 work. So attack your non-monic trinomial, you get 2 answers. Here is the biggest part for a point of inflection. Most people stop there because they think that's enough, I found my point of inflection. There's one at 1 1/3 and there's one at 6. You have not finished the testing. And if you don't carry on with the testing, you don't get all the marks. And the testing involves a table. So you can see there are 2 tables. The first one is for the 1 1/3. It is y double dash. That's another thing I noticed last week. When people were putting it into their test, they were putting the wrong thing in that particular row. It is definitely y double dash you are testing. And all you want to do is, when x equals a number lower than 1 1/3, test it out if it's positive or negative. Now again, all you see is a positive sign there, but someone did something to get that positive sign. It doesn't just appear. It's not just pure luck. You don't just say 50-50 chance. You do this calculation. Even if you do it on a calculator, that's fine, but you've got to do a calculation. And then when x equals 2, again, the same thing, even if you do it on a calculator and you come up with a negative number. Now, there has been a change in concavity. So because this shows that it went from a concave up to a 0 to a concave down, all right, that's a change in concavity. So this is definitely going to give you a point of inflection. And then it says the next one, test for the number 6. Again, put some numbers in, get the positives and negatives out of the way, even if it's just on your calculator. And again, there's been a change in concavity. If you don't get that change in concavity, then you don't have a point of inflection. Now, here's another important thing. It's amazing how many times people will, all that working so far has said there are 3 turning points and 2 points of inflection. And then when people go to graph it, what ends up happening is they throw in some extras. And the reason why they throw some extras in is because something has gone wrong with their number calculation. So see the 351, see the minus 1024. There are so many places that we could make a mistake. And when you go to put your clues together, the first one says there's a minimum at 0, 0, so I tend to do this minimum hat. There's a maximum at about 3, 351. Not drawn to scale, you just make it go up somewhere. There's another minimum at about the minus 1028. So again, it doesn't have to be drawn to scale as long as you dip it down a fair bit. Now for me to put those together, there are 2 points of inflection, which means there's some changing in concavity. So it says there's a point of inflection about there, and there's a point of inflection about there. Again, it doesn't have to be spot on because it's not drawn to scale. Join all those clues up, and you have got yourself the curve. Now that's where people go, if it's not joining up, then you must have made a mistake in your equation work somewhere. And then begins the problem of, where did I go wrong? Okay? So that's why you've got to get good at your equations and your substituting your values. All right, one for us to do. This is on page 17. Now there's a whole blank page. We've got to come up with all the facts first, and then we get to draw it, okay? So I've just got this one ready. X to the 4 plus 4x cubed. We go straight into, if this is my y, now I'm very much a labeller, so that means that I will put my y dash, and I'll find my y dash quite quickly. I'll find my y double dash quite quickly. I've got that out of the road, and it's all labelled. And again, do tell me if there's something not quite right there. All right, we've got to look for the stationary points. Automatic mode. First thing you do when you're looking for a stationary point or points, you go and put your y dash equal to 0. Now the reason why I tell myself this, you'll see it on my solutions, is because I want to make sure I pick the right statement. So I'm going for the 4x cubed plus 12x squared is equal to 0. Now that's an equation to solve. It's depending on my ability to factorise. Best thing I can do is take a 4x squared out of that. So you can see there are places that you might make mistakes. You want to try and minimise those places. I think I'm getting two answers, 0 and x equals minus 3. Now keep an eye on me, make sure I do all the right things while I'm connected up here, looking after all these bits and pieces. Now, at some point, you've got to find the y coordinate. So you can do it now, you can do it later. You can grab your calculators if you've got them. You tend to save time because the numbers can be awfully ugly sometimes. All right, so it says, your job is to say, when x is equal to 0, all right, what's the y value? All right, and when x is equal to minus 3, what's the y value? Now I'm just going to go straight to my calculator. I'm substituting in the 0. Now the 0 gives me just a plain 0, so I've got 0, 0 as my first point. The minus 3, what have we got for the minus 3? Any suggestions? What you get? Any suggestions? Minus 27, anyone backing me? Yeah, Alex? Yep, minus 27. Again, keep an eye on the substitutions. So it's going to be a minus 3 minus 27. Again, please check on those substitutions. Where did I get them? I went back to my y statement and I substituted the 0 and then I substituted the minus 3. Be careful if you're putting minus 3 to the power of 4. Make sure it's in brackets. We okay, Cassie, with that minus 27? Yep, all right. So there's two stationary points. Your job now is to tell me their nature. On that flow chart, the easiest thing to do to check its nature is use your second derivative. So we would always go for a second derivative unless it's too hard to calculate. Well, I've already got my second derivative in front of me there. So I'm going to say, and I always tend to talk to myself, at 0, 0, y double dash, and I'm going to actually show that it's 12 times 0 plus 24 times 0. And it looks like I'm getting a 0. Now, when your y double double dash gives you 0. I can't declare it to be a maximum. I can't declare it to be a minimum. So where does it get put?
Potential point of inflection.
Sounds good to me. Therefore, it's a potential or a possible, whichever word you like, potential point of inflection. And I'll test it out after when I do my points of inflection. So he's just been put on the shelf for a moment. He's not a max, he's not a min. The other guy, which is at -3, -27, I go check on its second derivative. I need 12 times -3 squared plus 24 times -3. And again, I just need to make sure and say, is that a positive number or a negative number? That's a 24. Positive or negative number? Positive. So because I've got a 36, it's a positive number, and because it's greater than 0, I draw myself a little, concave up to say this one is going to give me a minimum. Concave up, and it's a minimum. All right, so that's got our turning points mostly figured out. We've got our points of inflection to go to. All right, so up here I'll just start working. For points of inflection, again, I tell myself you want to make sure you take your second derivative and put it equal to 0. So I look for my statement. It says 12x squared plus 24x is equal to 0. By the way, I don't chance anything. I write it all down. I show every single thought I'm having because there's always that chance that something might go wrong. It looks like I've got an x equals 0 and an x equals -2 as points of inflection, or possible points of inflection, or potential. So what are we going to do to actually reinforce if they are or are not? What do we have to do? So I've just got here, putting it in capitals, these are potential points of inflection at this point in time. All right, so what I've got to do is then say that I'm going to do one for the x, for the first guy. Now you could put it all on one. I'll just separate them. And what I'm going to stress is this is the 0. This is the second derivative. And on my table, very clearly it says it's y double dash. That is going on the second row. Now I'm about to pick a number, all right, a number that's a bit lower than 0 and a number that's a bit higher than 0. So something like -1 there and potentially a 1 there. All right. So you're putting it into second derivative. Now again, even if you just do it on the calculator, all right, you might just substitute the -1 into the calculator and you'll end up with a positive or a negative when you put -1 in. Positive or a negative?
Negative.
Negative. Now that's all I really need to see. But people think that just comes automatically. I did it on my calculator and I'm going to do the other one as well on the calculator. Pick the number 1. Second derivative, positive or negative? Positive. So this one is okay. I'll just put a double tick there for a second. I'm also going to do the one called -2. So -2 there. Y double dash being tested. Pick a number above and below. Well, if you're sort of wise, I'm going to pick -1 because it's already been done above. So I'm saving myself a little bit of time. I already know that one is negative. And I'll pick another number down here. All right. Suggestions you can pick. A wise suggestion. Anyone who's paying attention? A wise suggestion. Easy one to save time. -3 because it's already done on the page. So I probably would go for -3 as well because I can see it was done down here to test out. And that's why when you do all your work, if your work is well labelled, you can already see that you did it down there and that the answer was positive. So these have both become points of inflection. So our job is therefore to go and find the y coordinate. So we've got to say that when x is equal to 0, what the y is, when x is equal to -2, what the y is. And again, on the calculator, if you need to go pushing it in, we already knew that one. So 0, 0 is a point of inflection. What kind of point of inflection is it? Because 0, 0 had its first derivative as well as its second derivative equal to 0. So it is a point of inflection, But there's something special about this guy. Anyone know the word that will go with it? The word that goes with it from last week? You're going to get tested on it, so I hope you're listening. There are two types of points of inflection. One can be a horizontal point of inflection, and one can be a non-horizontal point of inflection. So I want you just to go back to page 2. Go back to page 2. Go back to page 2. Have a look at the bottom. It says points of horizontal inflection. Now, point of horizontal inflection, can you see what it's going to look like? Now, I've got one of those. I'm not sure which one it is. It's going to be one of those coming up, and it's going to be at 0, 0. So I'm going to put here that this is a horizontal point of inflection. And again, I'll state to you, for those who are listening, why is it horizontal? Because its y dash and its y double dash are equal to 0. The other one, which I'm waiting for, minus 2, and what's its coordinate? So minus 2, and we've got, anyone got a suggestion for its y coordinate? Anyone get minus 16? Looking out there, any confirmations? Asher? No confirmation on that? Go on, check it for me before I go. I'd hate to put the wrong number in. Minus 16? I'll write it. Someone's going to check it for me and declare it very soon. This one is a non-horizontal. Now, you don't have to sort of stress it, but what you want to make sure you do is understand that they are different types of points of inflection. All right, so we need to draw this. So grab yourself a pencil and a ruler. I've got this space down here. All right, I've got this space down here. And I'm going to say, okay, I need 0, 0 as a point of inflection. I've got this minus 2, minus 16. Here's on the screen somewhere. I've got this minimum at minus 3, minus 27. So when you go to graph it, give yourself an idea that you need something down in the minus 3, minus 27. And the other thing to remember, people, you've done first semester maths. This is an x to the power of 4. Do you remember when we did degrees bigger than, 2s and 3s? I did a lot of disco dancing type of thing. So you should have an idea what an x to the 4, it's the leading term, it's positive, it's an even number. So what sort of disco dancing should you have? That's telling you what your graph is doing. Is it doing a bit of this? Is it doing a bit of this? You'll be amazed because even that little fact should come into this diagram. So here we go. We will have ourselves a diagram now. Without a ruler, I will go like this. Okay. Remember those x and y's. Please remember to label them. So you've got a 0, 0. Something's happening at the 0, 0. It's decided not to be a max or a min, but a horizontal point of inflection. Over at minus 3, minus 27 down here, there's a minimum. So I'll put minus 3, minus 27. There's a minimum cap going on there. And I know that 0, 0 is a horizontal point of inflection. So have a look back at page 2. It's got to be one of those. And I also know what an x to the 4 looks like. And I had a lot of people doing this at me, so you might not have seen behind you, but they're doing that. So they know where it should start and where it should end. So here we go. We're going to go down here, turn. Now this bit here, with a pencil, right, I say with a pencil because a lot of people just can't get the motion. This is a horizontal point of inflection, so I need it to go like that. So it's like the x to the 3 sort of curve. And then it keeps going up. Now, not straight up like that little bit just then. We'll get rid of that. So we'll go up, up, up like that. So it is going out like that. Now, if they would also like to know, let's check our points of inflection. Well, the 0, 0 is obviously horizontal. And there is another one about here. And you can't it doesn't stand out, but it's where your concavity should be changing from concave up to concave down. Okay, so this guy here was the minus 2, minus 16. Now, every single part of that agreed. So even when I was asking you to check my minus 16, this actually helps me say I think my minus 16 was correct, because otherwise it wouldn't be sitting right there. Now, it's only meant to be a sketch, so don't panic too much if it doesn't flow, but I can see the minimum, I can see the points of inflection, and we don't need those x-intercepts. So we do not need this guy here. All right, so don't go solving it. Now, it takes a fair bit. All right, it takes a lot of prep work, and if you go wrong in your equations, we have a problem. So, round 2. Let's have a look at round 2. There is a difference in this question, and it's getting you set up for what's coming, and it wants it to be in a restricted domain. Wants it to be in a restricted domain. So, before you go anywhere, what you might want to do, because sometimes people get so excited and they do the whole diagram, but this has got a restricted domain, so what we do make sure we've got is that we're coming back and the -2 will have a point and the 2 will have a point because they're telling me where to start this curve and where to end this curve. So this is actually telling me, yeah, you're going to do exactly what you did just a minute ago, but there's one extra accessory we have to check. It actually starts and finishes at a certain place. It will not have arrows on the end. So these will not have arrows on the end because I'm asking you to start from a spot and end in another spot. So that's the only difference. Now, if you want to figure those out now, you're most welcome to. So -2 has a partner, 2 has a partner. So I'm going to do those straight out. Okay, so figure those out straight away. So I've got that. What are people noticing when they get their answers? Anyone got some answers up there? I've got the same number, 15 and 15. Anyone else getting the same number? I'm looking out there. Now, that doesn't surprise me because also from first semester, in the back of my head, stored somewhere, I had some knowledge about even functions. And I know this is an even function, so I'm not surprised that these numbers, the -2 and the 2, gave me 15s because this is an even function. So I'm just sort of digging up old information that can become useful to you when you're graphing. Here we go. We want our usual. So I'm always talking to myself. Stationary points when the first derivative equals 0. I'm going to put it down and I'm going to factorise. Now, to me, it looks like this factorises again. So do you remember your difference of 2 squares? So I took out the 4x, and then I've got myself an x squared -1, and then I think that factorises again. This seems to be telling me there are 3. So let's have a look. I think one of them, this is always the one that people seem to forget and think it's not there. Again, if you only present me 2, your diagram will look very different, very strange. Your clues won't agree. People who drop that x equals 0 think there's only 2 points of 2 stationary points will have a slightly strange diagram coming out, if they get their diagram coming out. So we got 3 points here. So again, it's up to you. You've got the calculator next to you. What I need to do is I need to find what this is, I need to find what this is, and I need to find what this is. All right, now I'm limited in my space here. You've got a whole big page of white paper. Substitute the 0 into the original, into the y function. Substitute the 1. And if you're smart and you've heard me say that it's an even function, what happens once you know the answer for 1? You also know the answer for -1. So that's you saving time. That's you being wise with your knowledge. So if I put the 0 in, I get 7. If I put the 1 in, I get 1 -2 plus 7. I'm getting a 6, all right? So I'm getting a 6, and because I know this is an even function, I think the other one will also give me a 6, but you can always put it in if you're unsure or if you didn't see that it was an even. Now we've got to test the second derivative, so I'm trying to summarise down here. I've got 0, 7, so I'm going to say the second derivative is going to be 12 times 0 minus 4, which is an answer of minus 4, which is less than 0. And if it's less than 0, that means it's concave down. So it gives you a max. So I'll just put that there. But remember, you've got more room than me, so put as much as you need in there. Second derivative will be 12 times 1 squared minus 4. 12, which is 8, which is greater than 0, which means it's concave up, so it's a min. And second derivative, 12 times minus 1 squared minus 4. Same answer, same conclusion. So we've got a max, a min, and a min. A max, a min, and a min. Points of inflection, righto, go for that one. Points of inflection, or possible points of inflection when y double dash is equal to 0. I've got myself 12x squared minus 4 is equal to 0. So at this point, you can take out the 4 and get yourself a 3x squared. Oh, why would I do that? Wait a minute. Get rid of that. We'll go 12x squared is equal to 4. X squared is equal to dividing by 12. And I had someone do this the other day in one of the quizzes. People jump to the conclusion that it's a 3. They see the 12, they see the 4. But keep in mind that it's 4 on 12. So it's actually giving me a 1 on 3, not a whole 3. The other problem is this should give you 2 answers. And if you don't see 2 answers, you're not going to find me 2 points of inflection. So there must be 2 answers. We think it's plus or minus 1 on the square root of 3. Plus or minus, there's 2 answers. The square root, so leave it as a surd, don't put it in as a decimal. So it's not pretty, all right, it's not pretty, but we have to test them out. So here's what you can do. These are going to be potential or possibles, whichever word you want, potential point of inflection. Now, because one's a positive 1 on root 3, one's a negative 1 on root 3, you could also manage to, sometimes people have come along and they can use, the one that's on the left is minus 1 on root 3. And what you can end up doing, you can actually sort of merge the two together because whatever is bigger than this is also smaller than the next one. So I'm just going to show you that. So what I've done is, like before, if you use the same number, when it's bigger than the negative version, it's also smaller than the positive version, so you can save yourself a bit of time. I think I'll pick a 0, just to be wise. I think I'll pick a minus 1, and I think I'll pick a 1. In case you're not sure, go and find out what that value is. 1 divided by the square root of 3. It's about 0.577. So if you're wondering how was she so sure about picking, you know, I had a gut feeling it wasn't going to be a whole number. It wasn't going to be bigger than 1, so I've gone with that. This is what I'm testing. So I know it's 0 there, and I know it's 0 there. Now, why did I pick those numbers? Because I've already done some of the working out over on this side. I know what y double dash is at 0. It was a negative, so I'm going to put that in. I know what y double dash was at positive 1. It was 8. So that's a positive, which was exactly the same as that. So all I've done is merge 2 tables into one. Again, being economical, saving yourself some time in a quiz can be crucial to you. All right? So it looks like both of those have become points of inflection. So I'll just put a little tick there that there's been a change in concavity on both of them. Now our job is to find the minus 1 on root 3 and the 1 on root 3. Now you remember that little knowledge about it being even? Because it's even, I'm only going to find 1 and then I can use the knowledge for the other guy. So if I have to, this is what I'm about to do. Y equals 1 on square root of that to the 4 minus 2 times 1 on the root of 3 squared plus 7. Now you may not like your surds, you might want to put it in and see what happens to what happens when you put that to the power of 4. It's a decimal at the moment, but when you put that to the power of 4, all right, it came into being a very nice fraction. So you should know whether the surd will stay or go. So what I mean by that is, see the square root of 3? When you put it to the power of 4, all right, the surd disappears. If it had been to the power of 3, it wouldn't have disappeared completely, but to the power of 4 it does. So this is actually a 1 on 9 minus 2 times a 1 on 3 plus a 7. Now you can check that if you want on your calculator. So I have substituted that in, and I'm just about to put all of that back in. I'm only going to use my calculator. I don't have to do that manually. And I'm getting a 58 on 9. Anybody else for a 58 on 9? Otherwise known as about a 6 and 4/9, but I'm a improper person, so I'll leave it like that. So this is what we have. We have 2 points of inflection. Oh, I already wrote it up here, so I'll put the 58 on 9. I'll put the 58 on 9. So if you're not sure, that's going to give you about 6 and about 4/9, if you want to know that for when you go to do your diagram.
Lucia,
Yeah.
I put the 1 on the surd tree in the brackets and put it to the power of 4, and I couldn't, no matter how hard I tried to type it in, I couldn't get it into a fraction.
Is it coming up as 0.11111?
Yeah.
Okay. Your calculator, has it ever done that for you? Some calculators may not convert it. Our calculator does.
Depends on
what it was. So ours did. So I did the exact same thing, and it came out as 0.11111, and then when I hit my SD, it just did its own conversion.
Yeah.
So if anyone has an answer to that, that's a blue. What kind of calculator is that?
Sharp.
A Sharp, one of those blue versions. But it's okay if you just leave it as that. You know, it won't be major. Okay. So we've got to draw this up, and we're keeping in mind that we had a start and an end position as well. So here's what we've got. Just as a quick sketch, here's my x-axis and my y-axis. Do you remember all the information we have gathered? 0, 7, there is a maximum. So I'll put a maximum hat on this 0, 7. There is a minimum at about 1, 6. Now I'm just going to sort of bring him out a bit, and there's another one on the other side. And these are minimums. So as best as you can, put all that in your diagram. You have a lot more room than me. All right. So I'm putting that info together. There's a minimum, a max, a min. I also know that this was an x to the 4, so my knowledge from last semester tells me that it's a positive x to the 4, so I know where it starts and finishes. Now, normally, I'm about to do something. I'm about to sort of draw what I normally do, which is continue, continue, and continue. But we had a definite start and stop in this one. Now, they won't always be -2 to 2 or -3 to 3. They won't always be the same number on both sides, so keep an eye on it. But they wanted me to stop, okay, at about the start and stop, and that looks about the best. It turned out to be a good place to put my big fat dots there. This is -215, which agrees with our very top info, and this is 215, which is, again, it's even, all right? Points of inflection, if you've got space, you can sort of show your points of inflection. There's a little one there and a little one there. If you can show them, put them in, but my pen will come out, it's quite big, so put your points of inflection. You can point to it if you want in your diagram. But the important thing is it agrees. Do I think that the point 1 on root 3, remember it was about a 0.57 something, and it went up to 58.9. See how it said 58 on 9? See how it says 6 and 4/9? Well, I'll just point to it there, guys. That guy there, the y value was meant to be between 6 and 7, and it actually did agree. It is between 6 and 7. Now, if you do your calculations and something goes wrong on this, then when you get to these places, you go, oh, that's funny, because it doesn't agree with what my calculation says up there. So something is wrong. What we're not good at is we will all make mistakes, but as soon as I make the mistake, I know how to go, hang on, something's not right, and work backwards. So your job's to be good at that as well. All right, how are we going with that? So, stationary points, you're happy with, because it's pretty much a standard routine. Then we go into our points of inflection. Do you know how to test a point of inflection? And then, do you know the difference between the points of inflection? All right. These ones here are just non-horizontal. All right. A non-horizontal point of inflection, both of those there. We good to go? We are now over the page, and it says on page 19, you are now just coming up with absolute maximums and minimum values. And this isn't any great deal of work. We've actually just done a great example. And it just goes on to say that the absolute, sometimes they call it global, so we put that there because you might be looking up a different resource, another textbook, another website, and they might say global, but we call it an absolute maxima or an absolute minima, is the greatest or least value of the function in a given domain. So they will only ask you this if they have made you start and stop your diagram in a certain place. Because if it's got arrows on it, whether they're both going up or whether one's going up and one's going down, it's pretty hard to say what the maximum is when the arrow says this goes forever. So you should not be getting asked a maximum, all right, if there's an arrow on it. You know that it's got to have a restricted domain. And the thing that happens is sometimes we forget to restrict the domain, okay? So that's what ends up happening. So basically you can have a local maximum or a local minimum where the function has a greatest or least value there than at any other points near it. So we're about to see these two words put in action. Now, this particular one is just a plot. It's not in your books at all. All it's saying is it appears as though this is being restricted from -1 when x equals -1, and it looks like it was meant to go to 2. So it might be just a little bit off this screen, but we'll just play it from there. So you can see it started and stopped. And the idea is if someone said, what is the absolute minimum, then this guy here seems to have come in with the lowest y value, all right? And then when you get asked an absolute minimum, most people think it's going to be here. That's certainly a maximum. It's a local maximum, which means it's a stationary point max, but it's not the maximum value of this function in this given domain. So the maximum would have been whatever that number was up there. So that's why all those calculations of ours are going to play a very important role. If we don't put them in correctly into our calculator, something's not going to come out right. So the first guy here is just explaining about whether there's an inclusion or not an inclusion. Don't think you have to worry too much about that because we tend to include them at both ends. The first example on page 19, I'm going to flip through because it goes right through, but it does say now we're starting to see stories come about. So this is about a company that has found that the revenue over the last 7 months can be approximated by this particular function. And it says that t represents the time measured in months. So now we're starting to link stories, which is going to be part of our second half today. But I thought we better just make sure we throw it in here as well. So this is their revenue. This is a function that someone has modelled, all right, for them, for the revenue that they're going to make for the last 7 months. So it's a restricted domain, starts at 0 when they started, and it goes to 7, which is the 7 months later sort of time. And you can see there that they've done exactly the same. They've called it r as a function of t, so that shouldn't put anybody off. They've had to expand that out because for them to do a derivative, then they've been able to say, now the derivative of this, all right, turns out to be much easier to figure out. They've done all the same things we usually do. They've come up with that graph, and all I'm going to jump to is the bottom line that says that the maximum revenue happens All right, so the maximum revenue is the 35 million, and it happens after 2 months. You can see it from the diagram. And there's a minimum in this 7-month period. It happens in 2 places. So looking at your graph, you can see that there's a minimum at the very beginning when t equals 0, and also when t equals 6, exact same value. So on the actual diagram, okay, it comes up. I'll just get the diagram up on mine. So see this diagram? Here is the max happening at the t equals 2, and the revenue is 35 million. You can see the minimum happens there as well as there. It's the exact same value, all right, of 3 million. So it happened at 2 places. All right, so we are about to look for these. We're about to set our own up. All I'll do is, when you turn the page over, all I'll do for this example is I want you to graph it. So there is a nice big white space there. All the working's been done for you. And you might get a little bit of easy work because this guy's only got a power of 2. You should know what an x to the 2 is going to look like. So you should already know what this looks like. And it says find all absolute and local max and min values of y for this particular graph in this domain. And as I said before, the very first thing you might want to do is state that -5 needs a partner and that 5 needs a partner, because this is a graph that needs to stop and start. Now this is not an even function. I can tell you it's not an even function. So I need 2 values. They're not going to be the same number. So start plugging some numbers in, because we're not good at doing lots of calculations and doing them quickly. I want to know what the -5 answer is, and I want to know what the 5 answer is. Anyone got one of those answers? It's also on the page. 8 for -5. Try again. The -5 shouldn't give you the 8. Yeah, it's the other one. Yeah, so the 5 should give you the 8, and the -5 should give you? The -5 should give you? No, a 48. 48. Check it again. It's actually in the working, but I'm going to stress that you do it at the beginning, because often we forget to do that. We get carried away and we draw the whatever we've got, the curve. Now, it went on to do the usual, so it tells you you're going to find stationary points. You did the first derivative, put it equal to 0. You can see there that there's only 1, so it's a nice easy equation. So life won't be all hard. It's at 2 minus 1, and then they went and tested its nature, all there, and it's a local min, which did not surprise me, by the way, because I know what this curve looks like in my mind. It's a parabola, it's a positive parabola, so it should be a concave up with a minimum. But this is making sure that it all agrees with you. So what I want you to do is I want you to draw, okay, I want you to actually draw that in that white space that you've got. We've already checked the endpoints. All right. We've checked the endpoints. I think this gives me space to draw it. You've got the white space. You've got a minimum happening at 2 minus 1. So 2 minus 1. I do know that it should come down, turn around and go up. Now I may want to stop and start. So I sort of have gone, but I would normally have a pencil in my hand, so I'm able to rub bits out if I need it. Because it said I had to start at minus 548, so I need to be quite high on this one. So it's going to start up here at minus 548, and then it's going to say stop at 58. So again, even if it's not quite made to scale, as long as you are coming in lower than that. And a diagram helps you establish, do you have an absolute maximum value? Now, it's not, you don't declare it to be a point, it's a y value. So it's only going to be a number, not a point, okay? So the absolute maximum happens at this y value of 48, so we agree with that. The absolute minimum, the lowest y value in this given domain was minus 1, that's why it says that. And it also happens to have one local minimum, okay, and the local minimum of -1, same guy as this. Does it have a local maximum? There's no place on this curve where there is a maximum turning point, so it doesn't have a local max. So you're ready to go for the next two, all right? We may get one done in here, and then the other one we can do at home, all right? So first thing is, I can see this y equals x to the 4 plus 2x cubed minus 2x squared plus 7 wants a restricted domain. So if you want, you can start putting that down in your first part of the clues. You need to do it at some point. It may remind you. It may remind you. And then we've just got to get back on that usual path, which is y dash, y double dash, go through all the stationary points. We don't have to find any points of inflection, so I'll put that up here so that if you've got your head down, okay, I'll just put up here, for this question, there is no need for point of inflections to be calculated. So let's just go with y dash is equal to now, as soon as I'm writing this down, I can see that my equation is not pleasant, but if I take out the highest common factor, it will make life a lot easier. So I'm taking out a 2x. It should leave me with a 2x squared plus a 3x minus a 2 is equal to 0. How good are you at your factorising non-monics? And again, I will do this very quickly in front of you, but you have to say, how do I do my non-monics? How do I find it? I'll also pause and say, there probably are some people in this room who will fall back on the quadratic formula. Now, I can't stop you falling back on the quadratic formula, but it's going to take you a lot longer. I say that, that's because I already know how to do a non-monic very quickly. But you've got to train yourself. If you are taking a long time to get this non-monic, come up to the drop-ins and say, look, I just need to get better at that. That seems to be what's causing me to slow down. So your job is to do the factorising. I'm going to go with 2x and x. I'm going to go with a 2 and a 1, a positive and a negative. So I think I've got myself 3 points. Now, I just did that non-monic, okay, very quickly because I know a method that works. So your job is to say, I've had a big, long holiday, I can't remember. Go back and say, highlight that and say non-monic trinomial, exclamation mark. Do better, get faster. So I think I've got myself 3 answers, 0, a half, and minus 2. 0, a half, and minus 2. While I'm at it, I'm just going to summarise. I just need these 3 points completed. So a bit of work, and I'll do my y double dash. So I think it's a 0.7 on the first one. I've got to put a half in and I've got to put a minus 2. I've done the second derivative work, so I know if it's a max or a min. Again, I'm substituting. Again, you can't see all of that because I'm saving a little bit of space there. These are not just coming out of, just randomly. I've done them on the calculator. Same for you guys. Try them out. And if there's anything that we don't agree with, make sure you tell me. And has anyone got these y values? I'm getting 109 on 16, which is about 6.8125, if you want to leave it like that. And the good thing about these calculators, you can go back and change a number in the working out or retype it, whichever one you would like. Anyone else get a -1? Check on me. Check on me there as well. I'm looking out there. If anyone did any of those, keep an eye on it. Maxes and mins, we don't have to do a point of inflection. Yeah, Alex? I see. But the half is in. The half is in, but the -2 is out. You are so right. Alex is just pointing out that the -2 is out of our domain, all right? But sometimes you may or may not realise it. I've already done the working. I'm hoping that it still would be agreeing with my diagram, because I will be chopping it off. As Alex has pointed out, it's not part of our given domain. So here is our x, here is our y. The 0 gave us a 7. The 3 will give us, check on it, I get 124. Anybody else? Anybody else for 124? Yep. So we're in the 0 to 3. The 0 was going to be a max, so I'm just still going to put, actually, I would draw it back down here at the 0, 7. There is a min up here. Now I'm going to have a hard time. Something must have gone wrong. Something gone wrong in my calculations. See that 3 guy here? Oh, I know what happens. This is my min down here. Here is my min. It's going to be at a half and 109.16. So there's my min, there's my max. So it had another min over here at -2, -1. But as we've pointed out, you don't need to draw it because it's outside. So this would have been a max coming around and going up. And I then want to stop it at the 124 position. Yeah, Cara.
In this bracket that you've got like the half and then the 109 and the 16.
Yep.
How did you get 109 and 16?
I put the half back into the y.
Into the original one?
Into the original.
Thank you.
So tell me if anyone differed from that, but I think we got someone else agreeing with it. It was 6 point something or other. And it would agree with where it's sitting because it's under the 7. Now the question had said, so we've drawn it, and drawing it helps you see what would be, is there an absolute maximum? Is there an absolute minimum? Okay, in this particular question. Now an absolute means what would be the highest y value that you can see from your graph. So I'll put here, getting it ready, absolute maximum. And I need not a point, but a value, and I need an absolute minimum, and I need a value, not a point. Absolute maximum from our curve, what would you suggest? 124. Absolute minimum from our graph, I'm going to say the 109 on 16. It is the y value, all right? Nothing goes under that y value, and nothing goes above the y value of 124 in this restricted domain. Remember, if it had not been restricted, we would have had arrows on it, and it would have gone forever in both directions anyway. Alrighty? So are we good to have a break? We are having ourselves about a 7-minute. Let's go for. So 1/4 Alright, 1/4 because we have on. Comment about redemptions. Same as usual, guys, it hasn't changed. You will get your quizzes back and you will be able to redeem as soon as you can. Redeem. Many people saw how last semester the redemptions probably got them through, and you might need to rely on them a bit more because this course is obviously harder. So your redemptions, don't wait for it to be too late, all right? You know that at the back, this is the one where in the back of our lecture notes, our course reader, page 184, we know that the first redemption is actually due at the end of week 3. We forgot to put it in there. We didn't remember to print it, so we got you to put it in, all right? So you will get it back this week, but your redemptions are due by the end of next week. Okay, we're ready for the word problems. Now, here's where it says up the top, this is called Geometrical Applications of Calculus. This is where we really start applying our calculus to word problems. Now, you might say sometimes I can just guess the answer to these word problems, but the point is you've got to use calculus to back your answer, all right? So it's not just about the number, the answer you get, it's about reinforcing it with all the calculus. And they're going to start by using, all right, they're going to start by using, on page 22, it goes straight into an example, and there's a couple of words there you want to get used to, all right? So if you've got, say, 2 highlighters, it might be useful for you to use them because you're going to see the word constraint function and you're going to see the words objective function. So they're 2 things that I know you don't have to write those words down, but your job is always to say, there are 2 functions I've got to find. One is the constraint. That sounds like it's restricting me. The word constraint means it's restricting me. And then there's an objective function, which is what am I trying to do for this question anyway? So you'll hear the words. You might not like the words, but they do help you lock in into your mind, into your solutions, that there are 2 functions you need before you start doing the rest of the question. So this one on page 22 says, use differentiation to find 2 numbers which sum to give 20, so there's obviously a clue, and multiply to give a max. Now, it's not about just finding pairs. Like I could sit here and say, well, 1 and 19 add up to give 20, 2 and 18 add up to give 20. I'm not going to sit here and go through all the options because if you do that, you're forgetting that there are fractions and surds in your life. So when people go to that option, when they do the I'll just guess it, they usually just try positive numbers. So it's not about doing that. It's about setting up 2 functions, which means 2 sentences, algebraic sentences, for us to use. So the first thing it says is you've got to come up with 2 numbers. Let x and y be the 2 numbers. And it says that the sum is going to give 20. So x plus y must equal 20 is the constraint function. Constraint function means it's from the clues, and it's the clue that is constraining me. It's restricting me to any 2 numbers, but they must add up to 20. And then what my objective is that I'm supposed to try and get a maximum product. So they've just introduced the letter capital M. It's going to be the product of the 2 numbers. So this is my objective function. Now what you'll notice is you are trying to maximize M. So I'll say this clearly. This is what you are trying to maximize. And what I used to do when I did all these questions, if that is your objective, what you then need to see in your mind is if that's your objective, M is equal to x times y, at this point you don't think anything's wrong. There is nothing wrong with what you've just written, but sometimes people go, where am I supposed to go next? You are trying to maximize M, so in the mind I'm thinking I need an M dash and an M double dash. Now that sounds great. It's my plan up here in the side of my head, but I have another problem. Because if I want to do a derivative of M, I've got 2 variables. and that's going to cause a problem. So you can see that what they've then done is they've then said that we need to bring one variable, all right, we need to get a variable in this M statement. X times Y cannot be differentiated at this point because it's got two letters, X's and Y's. So our job is pause on do the derivative, just pause on it and say, one of you guys has to move. And that's when you go back to your constraint and you make one of them, and we've just chosen the Y variable, make Y the subject so that you can then do a substitution. And why are you doing that? So that the M is now equal to 20 times X minus X squared, and you now have a green light to do a derivative because you only have one variable. You only have X's in that line. So you cannot differentiate if you have two letters, two different variables. The plan is pause, go back to your constraint, make one of the letters, and we just happen to pick Y, the subject of it, bring it back in, all right, and then keep going, because now you can find your M dash. Now you can put your M dash equal to 0. You're finding your stationary points. So it's the same as usual. You are finding your stationary points when M dash equals 0. Once you solve that equation, it says when X is equal to 10. You have not finished just because you think you have found the variable's value, because you haven't proven to us that taking X as 10, or 10 as X, is going to give you a maximum. You have not proved with calculus that it's going to give you a maximum. To prove that, you do the second derivative. So the second derivative, when X is equal to 10, you go back to the statement. Now it says here that second derivative is minus 2. Now, it doesn't matter what X value you put in, the second derivative is always negative, which means this was always in a concave down phase. So this was always going to be a maximum. So I didn't have to substitute the X equals 10 because there was nowhere to substitute it. It is always negative. So you have made sure that you have come up with this support to why you think X equals 10 will give you a maximum product. And the question had said, find the two numbers. So the two numbers happen to be 10, and when you substitute the 10 into the Y variable, you get exactly the same number. So what it's saying is that the two numbers are 10 and 10. Now, in case you're not sure what you've just done, you could have picked any two numbers that add up to give 20. So I'll put what I said before, 0 and 20, 1 and 19, 2 and 18, and I haven't even gone into fractions and surds. What you have just done algebraically is come up with the two numbers that will give you a maximum product. Because if you multiply the 0 by the 20, you'll obviously get 0. If you multiply the 1 by the 19, you'll obviously get 19. If you multiply the 2 by the 18, you'll get 36. Now, the idea is you have done a really smart thing very efficiently. You do not want to go through all the numbers because there's physically no way you could ever go through all of the numbers. But this has said that the maximum will occur, the maximum product will occur when it's 10 and 10. Are you ready to go with the word problems? They vary, they're not all the same type, but they have one thing in common. They will all have a constraint function and they will all have an objective function, okay? So here comes ours. It says down the bottom here, a farmer wants to fence off a rectangular area next to an existing fence, which makes a difference. He's already got a wall on one side, so he needs the fencing to go along here, he needs the fencing to go along here, and he needs the fencing to go along there. He does not need it to go along the other existing fence. It says, what are the dimensions of the rectangle? So it wants to know how big to make that rectangle that will enclose the greatest area. He's got 300 metres of fencing, okay? So remember, he could make lots of rectangles, lots and lots of rectangles that he can come up with using 300 metres of fencing. He wants to know what he should make the length and the breadth if he wants a maximum area in that green spot, okay? So we want to start with a couple of variables. And it doesn't really matter. I'm going to go with, I'll call this guy x and this guy y. So we want to just say let x equal the width and y will equal the length. Now, can anyone see the first guy, the constraint function? What are we restricted to? We are indeed. There's our constraint. So what I will do here is our constraint function is that it's got 300 metres of fencing. So I'll put perimeter is equal to 300. Where's it going to come from? Because the wall's already there. So I'm going to need it to come from x plus y plus x is equal to 300. So in fact, 2x's plus a y is equal to 300. In case you're wondering, the fence has to go x plus y plus x, and that's how I got my 2x plus y statement. There's my constraint. Now, I'm not sure what to do with it yet, so I leave it there. There must be my objective. What am I trying to do? What is my objective? My objective is to find the greatest area. So I would like an area statement for a rectangle. Now, we're asking you some simple shapes. So a rectangle will be length times breadth, so x times y. Now, as soon as I've written that objective function, area equals x times y, because I'm trying to find the word greatest, it's like the maximum, I'm trying to find a maximum area. In my mind, I know I want to find a dash and a double dash. But I've got a problem. My a statement at the moment has got two variables. It's got x's and y's. So what do? I go back up to my constraint. I make somebody the subject. Who should you make the subject? Make a wise decision. You can make x the subject if you really want to, but a wise decision would be make y the subject because it's a lot easier to work with, like that. Go and substitute it back in so that this now says x multiplied by whatever your y statement is. So I've got 300 minus 2x. We are back on. That means we only have one type, so let's expand it out and get a statement. So 300x minus 2x squared. Now you get the green light. Start doing a dash and a double dash. So it all falls into place. It all makes sense that you needed to remove one of the letters. And if you can try and put the word constraint and objective into your vocab, it might help you out. The constraint is needed, and it's in the clues somewhere. Are you ready? Let's do the a dash and the a double dash. A dash, 300 minus 4x. A double dash is just a plain minus 4. How do you find a stationary point? All I need is stationary point, and this time I'm going to put a dash is equal to 0. Get good at solving equations. X is equal to 75. This is not where you stop. This is what a lot of people will do because it looks like I've solved it. I found x. You have not as yet with your calculus shown that making the x 75 will give you a maximum area. You must come back and show me that somewhere. So what you want to do, I'll just put it up here. Okay, so at x is equal to 75, a double dash, and it has no variable. It's always in concavity down position. It is always giving a max. So therefore, make sure you say the word that you are trying to prove. At x equals 75, the concavity is negative. Yeah.
Isn't it just a dash, not a double dash?
No, if you tried putting it into a dash, it'll give you 0. So if anyone by accident puts it into a dash, it's just sending you back and giving you 0, which is just why you got 75. So always a good thing if you say, hey, how come I got 0 out of that? And you shouldn't. In these questions, you shouldn't be getting a 0. A maximum. And the final thing is, make sure you answer the question, which is, what are the dimensions? And when you talk about the dimensions of a rectangle, you tend to say that x, which is its width, so the width is equal to 75, and it was in metres. And the length, now the length was given as y, and you've got a statement there that says y is equal to 300 minus 2 times your x value, so this is 150. Have I finished the question by answering what are the dimensions? So make sure you say, I have given them the width and the length, they're the right dimensions that we need. Now this has got a few, we've got two more to sort of practice with. Each one varies in its story, all right? So they're all very different. I think a diagram helps you, all right? Establish what it is you're trying to figure out. Now, the next one's worked for you, but I'm still going to go through it because it can also create a problem, especially if you don't understand the words and you don't know how to make a diagram appear. So sometimes it's more the comprehension of it. Here's what it says. A magazine ad is to contain 50 centimetres squared of text, which is that grey colour, with clear margins of 4 centimetres at the top and the bottom, and 2 centimetres at each side. Now, we've given you a diagram, but in the tutorial, in the actual exercise in this book, there are no diagrams, I think, except for one little starter, but otherwise there's no diagrams given. So sometimes it's up to you to figure out what a diagram, you know, would look like. So give yourself a rectangle. The text is in the middle. The 4 is on the top and the bottom, so that's why it's here and here. The 2 is on the side, and what they've established is that the x and the y are going to be the dimensions of that text. So if you follow it through, it says, first of all, you've got your constraint. The constraint said that it has 50 centimetres squared, sounds like an area of text, so the constraint is that x times y is equal to 50. Not sure what to do with it yet, but that's the constraint. And then when I wanted to say what's the objective, it's to minimise the total area of the ad. So to minimise the total area of the whole page, of the whole ad, it says the area of the bigger rectangle would be x plus 8. Can you see where the 8 comes from? Top and bottom. Multiplied by y plus 4 from the left side and the right side. And again, there's your objective, and it would be fine, except it's got two variables in it. It's got x's and y's. Now, at some point, you can either do this multiplication here. You could have expanded this x times y if you wanted to before, or you can put the y in first. It doesn't matter whether you do it first or second, but at some point, you have to expand this as well. So you can either expand it before when it still had y's in it. If you expanded it before, it would have said xy plus 4x plus 8y plus 32. And then you could have brought the y in, so you will still get the same as down on the bottom here. Okay? So this is what we've got. And you'll notice a couple of things. Keep an eye out that when you go to do your derivative work, you need your x to be in index notation. So see this 400 over x? I have to make sure I can adjust. There are some trickier ones along the way, but keep an eye on some of those. A dash gets done, A double dash, oh no, up there, A dash is equal to 0, and then it goes through and it solves this. There are two values when you take a square root, and it's still important to say there are two values, because if this had been a curve that you had been drawing, you would have needed the plus and the minus 10. So don't ignore the minus 10, but say there should be two answers, plus or minus, but then at the actual 10, at the minus 10, sorry, it's not valid for the question we're doing because we're talking about x being a distance, so you can't have a minus 10. So don't just rub it out, don't just make it disappear off your page. Actually tell them why minus 10 is not going any further in your calculations. So the only thing they went forward with was the x equals 10. They checked that it was a minimum, so it has to be there somewhere on your page. And then they've come back and told the overall dimensions. Okay, so they needed to know what x plus 8 was going to give and what y plus 4 was going to give. So make sure you finally answer what they wanted, not just give them an x and a y. It's not where they want you to stop. Over to you guys. Here we go. We've got 2 to go. First of all, you might get asked to draw something from first semester. This question says find the dimensions of a rectangle of the largest area which can be inscribed. Now, inscribed means put inside of, right? So I've got the inscribed under control. Where am I trying to draw this rectangle? Inside what we call the closed region, bounded by the x-axis, the y-axis, and a curve that we haven't seen for a while. Y is equal to 8 minus x cubed. Over to you. What does that look like? Think back to last semester. What does an x cubed look like? What does a minus x cubed look like? And then add an 8 to it. So, give me a diagram. So, here we go. Give me a diagram. Mine's looking something like this. It's going to come in there at 8. Something like that. That's what I want to draw. Now, it's not crucial, but you get a better idea of what it is you're doing if you can draw it. Now, we're supposed to be putting a rectangle in the region that is bounded by the x-axis, the y-axis, and this curve. So we're going to try and put a rectangle in there. So I'll just put a dotted. I'll just go dot, 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 like that. And those dots, there's a point right there, and it's x across and y up. I don't know what those numbers are yet, but that's what my job is. My job is to try and find, all right, the dimensions of the biggest rectangle I can put in there. All right, anyone want to start me off on the constraint? Where is the constraint function in this one? Any ideas? What are we constrained to be in? Y equals 8 minus x cubed. We are constrained that that point there, if you want to call it P, xy, that point is constrained to being on that curve. What is it that we are trying to get to? What's our objective? To have a rectangle with a maximum area. Have a look at that rectangle you've drawn. What would you put? Remember that this point x, to get to this point x, you go x across and y up. So what are the dimensions of that rectangle? So it's gone x across and it's gone y up. So the rectangle has gone x across and y up. So the objective is find the area of the rectangle, which is x times y. So we've got a constraint, we've got an objective. And then normally I hear myself say, well, if I'm trying to maximise area, I think I'm going to need an A dash and an A double dash. And then you say, I've got a problem, I cannot proceed because my A has got 2 variables. So here's what we do. We go back to the first one, and it already has y as the subject. So it's going to be x multiplied by, and I've substituted the y value. So the first job is to substitute the y value. This now gives me that the area will be 8x minus x to the power of 4. And once you see the all clear, there is only one variable. There's only x's in that statement. So let's go for the A dash and the A double dash. So you've got the green light. Once you can see there's only one type, go for it. It's going to be 8 minus 4x cubed, and this guy is minus 12x squared. All right, back to our usual. We have to go find stationary points because that's what we're trying to do with our calculus. Yep. So this guy here, Cara, is this guy here, but this guy has 2 variables. It's got an x times a y. So you're okay with that statement? Because you have to make that statement yourselves. You can't find an a dash. You can't find a derivative of that statement because there are two letters. And you can't go ahead. You just can't go and do a derivative until you've got just one type. So you do a substitution. From your constraint function, see how it says y equals 8 minus x cubed? You bring that one into your area statement, and now it says x multiplied by. It used to say multiplied by y, but now it's got multiplied by 8 minus x cubed in a bracket. You have to expand it, unless you plan on using a product rule, which I don't think I want to. And then you're back on track, Cara, because now that statement A has only got x's in it. All right? So a dash equal to 0. If you've gone ahead, 8 minus 4x cubed is equal to 0. 8 is equal to 4x cubed. X cubed is equal to 2. What will I put down as an exact value? Exact value? Cube root of 2. There is only one value. It's not like a plus or minus in this case. So the answer is the cube root of 2. I cannot stop there because I think that's going to give me a maximum area. But to convince people, what you need to do is say that a double dash is equal to minus 12 times by. Now, it doesn't really matter what, if you know what that should be. You can put it in on your calculator. But minus 12 times anything squared will always be still negative. So this is going to be a maximum, but you can check it on the calculator. It will be a negative number. So I've checked that it gives me a maximum. That's part of your marks when you set them out for us. And the question said find the dimensions. So what I've got to do is go back and find the dimensions. X is going to be the cube root of 2. Y is going to be, now I have a statement up there that says it's 8 minus whatever x is, cubed, and when I push that in, I'll end up getting a 6. So the dimensions are cube root of 2 by 6. They're the dimensions, if you want to give it to us like that. The cube root of 2 by 6, or times by 6, as its dimensions. Yep, Cara. That one there, 8 minus the cube root of 2 cubed. And the cube root of 2 cubed gives me back 2, so 8 minus 2 is 6. That's how come I got that. All right. And there's one more for us to solve. And again, there's a couple of old thoughts you might need. We're hoping that they're pretty basic. When we get you to come into our courses, we sort of say some assumed knowledge. Are we ready to go for our last one? Consider a rectangle of perimeter 12 centimetres. All right. So I'm going to draw myself a rectangle of 12 centimetres. Now, I've got myself a little x happening and a little y. So even if time is against me in an exam, I will write the very first, okay, I will write the very first constraint function. What's the constraining function here? Constraining function. What do you think it would be?
2x plus 2y equals 12?
Yeah, putting the 12 into that diagram somehow. A perimeter is the distance all the way around, making sure you remember that that's an x and that's a y. So 2x plus 2y is equal to 12. Now, I'll leave it there. I'll come back to it. I'm sure I'll need something from it. Now, here's the thing. It's going to form an open-ended cylinder using that rectangle. Think about a piece of paper and how when you get a piece of paper, all right, there is one thought here that you may or may not remember, but when you get a piece of paper and you make it an open-ended like this, all right, I need you to figure something out, all right, because it says it's going to make a cylinder. What dimensions of the rectangle, so what should x be and what should y be, which will result in a cylinder of maximum volume. Okay, let's see what happens here. This is my objective. We'll see if we can remember it bit by bit. What's the volume of a cylinder? Round 1. Volume of a cylinder. Area of the base times the height. Area of the base times the height. What kind of shape is at the base? Circle. So what's the area of a circle? Pi r squared with a h, meaning how high the cylinder is. Now that's the formula. Now we've got to figure out from this which one's going to help me get my r and which one's going to help me get the h. Any suggestions on the h? The h is easiest. The h, watch what happens. This is my x along here, so that goes to form the circle, but the height comes from this side. So can you tell me what the height will be? Yep, the height is equal to y in this story. How do I get my radius? So think back, there's another bit of a story that you might need to dig. What do you call that part of the circle that goes around the outside? Circumference. What do you know about circumference? So, no, just 2 pi r. I hope you stopped at the r. 2 pi r. 2 pi r. And it's got to make up how much? Well, it's actually got to be aligned with the x. So we want 2 pi r to equal the x distance. So what's the radius going to be? X over 2 pi. Now we've got ourselves something to substitute for r. We've got something to substitute for h. So that's probably the hardest part, digging all that up in your mind. So here we go. Volume will now be pi times by the r, so I'll substitute and I'll square, times by the height, which is y. Now you can sort of see where this is going. It's not as pretty as the others, so it's got a little bit more work to do. I'm going to expand this. Leave the y where it is for the moment. I'm going to expand it. Pi times by x squared on 4 pi squared times y. Tidy it up a bit. On the top, I've got a x squared. I've got a 4 with only a pi on the bottom. Now that y can sit anywhere, but you can. I've placed him over there because you can see that what sometimes happens in people's brains is there are 2 variables there. X is variable, y is variable. Pi is not a variable. Pi is a constant. So when I say, the same as usual, our objective has got 2 variables. It's got x's and it's got y's. Someone's got to go. So go back to your constraint, and from your constraint, okay, so from the constraint, I had 2x plus 2y equals 12. 2y equals 12 minus 2x. Y should equal 6 minus x. So that will be going in place of y. So you could do it before, you can do it now, as long as at some point your volume has now got a v equals x squared with a 4 pi, and instead of y, I'm going to put a 6 minus an x. All right, so I have to do this. Check. It's just got x's. It's not pretty. A lot of people won't like it, but it's just got x's. So do some expanding. So what we'll get is 6x squared on 4 pi minus x cubed on 4 pi. Keep in mind that the pi is just a constant, like a number. If you want to fix that up a bit, you can go to 3x squared on 2 pi minus x cubed on 4 pi.
What's that y doing?
What's that y doing? That y there?
Yeah.
He's being replaced. He's being replaced.
So it's on the line?
Oh, he's just being, yeah, he's multiplied. He can be on top, he can be next to him, but it doesn't really matter. It's one or the other. They're both the same. I just pushed him over a bit so that you realise everything else has got x's and constants. The y is going to get replaced.
Yeah.
Now
Okay.
your job is to do v dash and v double dash. Now it's not as bad as it seems, because remember, the 4 the pi, the 2, they're constants. All right, they're just constants. So I've got another page after this, so I have to turn over. Are we ready to go? Can I flip? All right. So this is where we were. We're at this point. I'm going to do my v dash is equal to. I'm just going to put the 3 with the 2 pi and make people see that the 3 with the 2 pi is a constant. And when I ask you for the derivative of x squared, that dot means a multiplication, so I'll put times 2x. And I'll do the same with this guy. I will first of all put the constant 1 over 4 pi, just waiting, and the derivative of the x cubed is actually 3x squared. So I'm getting, if it lets me write down here, 3x on pi minus 3x squared on 4 pi. Now I need to do a v double dash. The first guy's got an x in it, so v double dash is 3 pi. I've got to turn that page over. And the other guy was going to come out to be 6x on 4 pi. So sorry, if you have to look back at the lecture, I'll just go, this is what was down the bottom here. Do a derivative. All right, so it does actually come out to give those two statements. All right, back to our normal position, stationary point, and it may sound like it's going to be horrible. Your v dash will say 3x on pi minus 3x squared on 4 pi. Now I'm just going to remind you of a couple of things. That is my first derivative equal to 0. That is an equation now. I can make life easier by multiplying everything by 4 pi because it will make all my fractions disappear. So what is about to happen, I'm about to multiply by 4 pi because that's an equation now. So it leaves me with 12x minus 3x squared equal to 0. So I've implemented this, righto, and that's what I've got. So in case you're wondering, how did that magic happen? And am I allowed to? Of course you are if you've got an equation. You now go into factorising, and it gets you two answers, x is 0 or x is 4. Now the x equals 0, it's not wrong, but x is the length of your rectangle. Not much good if you've got a length of 0. So I'm just going to say in this question this is not going to go any further because it's a 0 value for a length. So the only one I'm going to test is this one. V double dash at this point at 4 is equal to 3 on pi minus 6 times 4 on 4 pi. Put it into the calculator, see if it's positive or negative. Turns out to be negative, so therefore I must see that you have put that into place, that the volume is a maximum at that position. And the question said, what are the dimensions of the rectangle? We need an x and we need a y. So we've got an x is equal to 4. And our y statement was 6 minus x. If you look back to your constraint and how we made y the subject, 6 minus 4, which is 2. So the rectangle, all right, would need to be, all right, 4 centimetres across and 2 centimetres high to make a open-ended cylinder with a maximum volume. Okay, that is actually what you've done. A 4 centimetre by a 2 centimetre rectangle. And you've done it algebraically. Now you're going to get hit with a few more in the tutorial as well as this book here. You have to set your own up, and so you have to practice. And basically come to the drop-ins. See if you can timetable yourself so that you can get some things done effectively, okay, for the second semester.